In this module, you will learn about sets and the representation of a given set. In our daily life, we encounter different collection of objects, such as a box of pencils or a bunch of flowers. Similarly, in mathematics, we often encounter different types of collections, like a collection of numbers on a real line, or a plane figure, which is a collection of points on a plane, and so on. We can refer to these collections as sets if these collections are defined well. A set is a well-defined collection of objects. By well-defined collection, we mean that we should be able to decide whether a particular object belongs to a definite collection or not. To understand this better, let's consider a circle on a plane. In this plane, we can certainly define which point belongs inside the circle and which does not. Here, we can say that the circle is a well-defined set of points on a plane. Another example of a well-defined collection is natural numbers less than 5. This collection of natural numbers is well-defined, as we can definitely decide whether a given particular number belongs to this collection or not. An example of a set that is not well defined is a set that consists of clever students. This is not a well-defined set because the choice of clever students is not clear, since there is no accurate measure for cleverness. A set is always denoted with a capital letter. The elements of a set are denoted with small letters. The word element is used synonymously with the words object and member. Consider the set shown here. The set is denoted with the capital letter A. The elements are denoted with small letters The element P belongs to set A. We denote this with the following symbol. Any other element, say Z, which does not belong to set A, is denoted as shown. The following are some special sets that are commonly used in mathematics to represent various systems of numbers. There are two ways of representing sets. The first is the roster form. The second method is called the set builder form. First, we will look at the roster form. This method of representing sets is also called the tabular form. Suppose there is a set of prime numbers less than 10. The prime numbers less than 10 are 2, 3, 5, and 7. To represent this set in roster form, we simply start with a bracket. List the elements and close with a bracket. Let's name this set as P. Similarly, a set of natural numbers between 20 and 30 is represented as shown. It should be noted that the order of the elements in a set is immaterial. So, set A can also be written as shown. While representing a set in roster form, the elements are generally not repeated. For example, let's take the set of the letters of the word trigonometry and represent them in roster form. In the representation, the elements TRO are repeated. So, this set can be represented as shown with the elements T, R, and O written only once. So, only the distinct elements are written while representing a set in the roster form. While we just simply list the elements to represent a set in the roster form, the set builder form is a more concise form of a given set. Let's use the same example that we have seen previously. We have a set of numbers 2, 3, 5, and 7. In this set, every element is considered equal to a variable x. Now we start writing the set in the set builder form. We start with a bracket and write the variable. Then we place a colon. We assign a property to this variable. If we observe, the numbers are all prime numbers. Added to this, every number is less than 10. Thus, we can write the set as shown. Each part of this representation is as follows. X represents each element in the set, and the statement is the property that defines the set. We name this set as P. We read this as P is the set of all x such that x is a prime number less than 10. As another example, let's represent the set of natural numbers between 20 and 30 using the set builder form. Here is the set of natural numbers between 20 and 30. Here, we consider any element in the set as n. N is a natural number, and n lies between 20 and 30. We name this set A. We read this set as follows. A is the set of all n such that n is a natural number, and n lies between 20 and 30. In this module, you will learn about different types of sets. A set is a well-defined collection of objects. We encounter various kinds of sets in mathematics. These sets are classified into different types based upon the properties exhibited by them. We will understand these properties by taking some sets. Let's consider a set as shown. The elements of this set are 1, 2, 3, and 4. The number of elements in this set is 4. This is a finite number. Sets having a finite number of elements are known as non-empty finite sets. If the number of elements in a set S is a natural number, then S is said to be a non-empty finite set. Next, let's consider a case in which a set doesn't contain any elements at all. For example, let's consider the set as shown. This set consists of elements that are real roots of the equation x squared plus 1 is equal to 0. Let's find the real roots of this equation. As we can see, the square root of a negative number does not exist in real numbers, and hence, there is no existing real solution. Therefore, there are no elements in this set. We can say that the set is empty. A set that does not contain any elements is called an empty set, null set, or a void set. An empty set is denoted by the symbol phi. So far, we have seen finite and empty sets. Now, we will see sets that contain an infinite number of elements. For example, let's consider this set. The elements of this set are natural numbers that are infinite in number. A set that is empty or consists of a definite number of elements is called a finite set. Otherwise, it is called an infinite set. We compare two lines by their lengths. However, while comparing two sets, we should consider the number of elements as well as the type of elements in them. For example, let's compare the sets shown here. The elements of set X are obtained by solving the equation a square minus 1 is equal to 0. Therefore, the elements of set X are minus 1 and 1. The elements of set Y are obtained by finding the odd integers between minus 2 and plus 2. The odd integers are minus 1 and plus 1. Therefore, the elements of set Y are minus 1 and 1. If we compare sets X and Y, the number of elements in each set is 2, and each set consists of same type of elements, minus 1 and 1. We can therefore say that sets X and Y are equal since both have the same number as well as the same type of elements. Two sets A and B are said to be equal if they have exactly the same elements. Otherwise, the sets are said to be unequal. To understand this better, let's take two sets, A and B. Both the sets have the same number of elements. However, the elements of these two sets are different. We can say that these sets are not equal to each other. As another example, let's consider two sets as shown. Set X consists of the letters of the word God. Set Y consists of the letters of the word good. While representing a set, we do not repeat the elements. Therefore, set Y consists of only the letters G, O, and D. If we compare sets X and Y, they have the same number of elements. Also, each element present in set X is also present in set Y. We can therefore say that sets X and Y are equal. In this module, you will learn about subsets, supersets, parsets, and universal sets. Suppose we have two sets, A and B as shown. The elements of set A are also present in set B. So, we can say that the elements in A are contained in B. In other words, we can say that set A is a subset of set B. This is symbolically represented as shown. This symbol represents subset. We can say that a set P is a subset of set Q if every element of P is also an element of Q. Symbolically, the definition of the subset can be represented as shown. The highlighted symbol denotes the word implies. This statement is read as follows. P is a subset of Q if X is an element of P, which implies that X is also an element of Q. If a set P is not a subset of set Q, we can represent this with the help of the symbol shown. If every element of set P is contained in Q and vice versa, then sets P and Q are equal. If every element of set P is present in set Q, we can say that set P is a subset of set Q. We can also say that set Q is a subset of set P. Therefore, set P and set Q are equal to each other. This can be defined symbolically as shown. The highlighted symbol means if and only if. The next observation is that every set is a subset of itself. This is symbolically written as shown. The third observation is that if a set A is a subset of B and A is not equal to B, then A is called a proper subset of B and B is called the superset of A. If any set P contains only one element, then P is called a singleton set. An empty set is a subset of every set. Since an empty set has no elements, it is a subset of every set. Now, let's observe some sets built using the elements of a given set. We have a set of elements as shown. Let's form new sets with a combination of the elements in this set, taking one element at a time. We have these sets. Taking two elements at a time, we have these sets. Taking three elements at a time, we get this set. Taking 0 elements at a time, we get a null set. All these sets are the subsets of set S. We form a set with the newly formed sets as its elements. This set is called the par set of set S. This set is denoted by P of S. The number of elements of this set is 8. We can say that if a set S consists of m number of elements, the number of elements of the par set is equal to 2 par m. The collection of all the subsets of a set A is called the par set of A. It is denoted by P of A. In P of A, every element is a set. Let's see an example of a par set of a set B. Taking one element at a time, we get these sets. Taking two elements at a time, we get this set. Taking 0 elements at a time, we get a null set. Taking these sets as the elements for a set, we get the par set of set B. The number of elements in set B is 2. The number of elements in the par set of B is equal to 2 square. That is 4. In some situations, we may have to identify sets based on the context. Consider a set of natural numbers. This set is a part of another set, that is, the set of real numbers. In this context, the set of real numbers is the universal set. Similarly, for the set of integers, the universal set is the set of real numbers. Let's take another example. Any plane figure, such as a circle or a square, is made up of points. We can say that for all plane figures, the Euclidean plane forms the universal set. Let's apply the idea of subsets in the context of real numbers. We know that integers, natural numbers, whole numbers, rational numbers, and irrational numbers together form real numbers. In set theoretical representation, we will explore how these sets are represented. The set of natural numbers is a subset of whole numbers. The set of rational numbers is a subset of the set of real numbers. The set of numbers we have seen are well known to us. We will see some conventions that will help us to understand sets that consist of any number of elements on the number line. On the number line, each point represents a number. For example, let's consider the real numbers in the interval between the numbers 2 and 3. 4 types of intervals can be considered with these 2 points as the endpoints. The first interval includes the numbers 2 and 3. This interval consists of all the numbers between the numbers 2 and 3. In set builder notation, the interval is represented as shown. The second interval is all the numbers within the interval 2 and 3, excluding the number 2. This is represented in set builder notation as shown. The third interval is all the numbers within the interval 2 and 3, excluding 3. This interval is represented in the set builder form as shown. The fourth interval is all the numbers within the interval 2 and 3, excluding 2 and 3. This interval is represented in the set builder form as shown. Of these sets, the set including the numbers 2 and 3 contains the greatest number of elements. With the observation, we can define some sets of real numbers. The interval 0 to infinity, with 0 included, is the set of non-negative real numbers. The set shown defines the set of negative real numbers. The set minus infinity to infinity defines the set of real numbers. On generalizing, we can conclude that the set of real numbers in the interval between 2 numbers a and b, including a and b, is defined as shown. Similarly, other sets of real numbers are shown. For all the intervals shown above, b minus a is the length of the intervals. In this module, you will learn to represent sets using Venn diagrams. A Venn diagram is a visual representation of sets. The concept of Venn diagrams was introduced by an English mathematician, John Venn. Venn diagrams are represented with the help of closed figures such as circles, ellipses, and rectangles. Let's draw a Venn diagram for the sets shown. We represent each set within a circle. The circle representing A consists of the elements 2, 5, 6, and 7. Each number is represented with a dot, with the respective number written next to it. The circle representing set B consists of the elements 3, 8, 9, and 10. One of the universal sets of these 2 sets is the set of natural numbers. So we include these 2 circles in a rectangle that represents the universal set, that is, the set of natural numbers n. Now, the Venn diagram is complete. Sometimes, we may need to represent 2 or more sets having common elements using Venn diagrams. For example, A is the set of prime numbers less than 10, and B is the set of prime divisors of 26. The collection of elements of sets A and B are as shown. These sets are represented in circles A and B as shown. If we observe, the element common to both the sets is 2. So we overlap the circles on each other as shown. The common region of the 2 circles will have the element 2, which is common to both the circles. In this module, you will learn about the different operations that can be performed on sets. While we come across many sets in mathematics, it is evident that many sets share the same elements. We can perform various operations on sets. Examples of operations are union of sets, intersection of two or more sets, difference of two sets, and complement of a set. Let us learn these operations in more detail. Let P and Q be two sets. The union of sets P and Q is a set that consists of the elements from both the sets. Let's perform the union operation over sets P and Q. The elements of sets P and Q are listed out one by one. The repeated elements are written only once. Here, 5 in both the sets is written only once. Hence, set P union Q consists of all the elements of sets P and Q. The definition of union can be as follows. The union of two sets A and B is set C, which consists of all those elements that are either in A or in B. Symbolically, the union of sets A and B is represented as shown. The Venn diagram representation of two sets A and B is as shown. The shaded region represents the union of the sets A and B. Observe that both the circles are shaded since set A union B consists of all the elements of sets A and B. Some of the properties exhibited by the union of two sets are as listed. The union of two sets follow the commutative law. The union of three sets follow the associative law. The result of the union of a set with a null set is the set itself. The union of a set with the same set follows the idempotent law. The union of a set with the universal set results in the universal set itself. Let's discuss the intersection of sets. Let's consider the same sets P and Q, which we saw before. If we consider the set of common elements of sets P and Q, then we can say that the set is formed by P intersection Q. In sets P and Q, the common element is 5. Therefore, the intersection of sets P and Q is 5. The definition of intersection is as follows. The intersection of two sets A and B is the set of all those elements that belong to both A and B. Symbolically, the intersection of sets A and B is represented as shown. The Venn diagram representation of intersection of two sets A and B is as shown. The shaded region represents the common elements belonging to the two sets. Here is an interesting property of the intersection of sets. Let's consider two sets C and D. We can observe that there is no common element among the sets C and D. Therefore, C intersection D is a null set. We can say sets C and D are disjoint sets. The Venn diagram representation of sets C and D is as shown. Some properties of the intersection of two sets are as follows. The intersection of two sets follow the commutative law. The intersection of three sets follows the associative law. The intersection of a set with a null set results in the null set. The intersection of a set with the universal set results in the set itself. The intersection of a set with itself follows the idempotent law. Intersection is distributive over union. This property can be verified with the help of Venn diagrams. Taking the left-hand side, for B union C, we have this Venn diagram. A intersection B union C is as shown. On the right-hand side, the Venn diagram for A intersection B is as shown. The diagram for A intersection C is as shown. For A intersection B union A intersection C, the Venn diagram is as shown. Next, we will discuss about the difference of two sets. Consider two sets X and Y as shown. The difference of sets X and Y taken in the same order is denoted as shown. The difference of sets Y and X taken in the same order is denoted as shown. First, we will find the difference of sets X and Y taken in the same order. This means we have to find the elements that are present in X but not in Y. The elements that are in set X but not in set Y are 2, 3, and 4. Therefore, set X minus Y has the elements 2, 3, and 4. Next, we find the difference of the sets Y and X taken in the same order. This is found by taking the elements that are present in Y but not in X. These elements are 7 and 8. We can observe that X minus Y is not equal to Y minus X. Set X minus Y is represented through a Venn diagram as shown. Observe the shaded portion. Only the region of set X, which is not shared by set Y, is shaded. Similarly, the Venn diagram for Y minus X is shown here. Only the region of set Y, which is not shared by set X, is shaded. The difference of any two sets, A and B, taken in order, is represented symbolically as shown. Similarly, B minus A is written symbolically as shown. The concept of the difference of two sets can be extended by replacing one of the sets with the universal set. Let's see an example to understand this. Let us consider the set of natural numbers. We can consider the set of whole numbers a universal set for the natural numbers. The difference of sets W and N is the complement of set N. The complement is denoted as shown. Therefore, the complement of set N with the universal set being the set of whole numbers is a singleton set with 0 as the element. Let U be the universal set and A be a subset of U. Then, the complement of A is the set of all elements of U that are not the elements of A. The complement of a set A is symbolically represented as shown. The Venn diagram representation of the complement of a set is as shown. The shaded region represents the complement of set A. It should be noted that the complement of a set depends on the universal set. For example, let's find the complement of the set of natural numbers with the universal set being the set of integers. The complement of set n is shown here. A few observations on complements of sets. If A is a subset of the universal set U, then its complement A' is also a subset of U. The complement of the union of two sets is the intersection of their complements, and the complement of the intersection of two sets is the union of their complements. These are called De Morgan's laws. The complement laws are as follows. The law of double complementation says that the complement of any set is the set itself. The laws of empty set and universal set are as shown. In this module, you will see how the knowledge of sets can be applied to solve practical problems. We have already seen the operations performed on sets, such as intersection, union, and difference of two sets. Let us verify some results based on these relations. To begin with, we will verify the relation n of A union B is equal to n of A plus n of B, provided A and B are disjoint sets. Let's verify the relation using an example. Let's consider two sets A and B. These sets are disjoint sets since there are no elements in common. The number of elements in set A is 4. The number of elements in set B is 5. The union of the sets consists of the elements as shown. The number of elements in the set A union B is 9. Now, we can see that the number of elements in set A union B is equal to the sum of the number of elements in sets A and B. Therefore, the relation is verified. Next, we will verify another relation shown here. The relation holds provided sets A and B are finite sets. Let's verify the relation with the help of a Venn diagram. From the figure, we can observe that the sets A minus B, A intersection B, and B minus A are disjoint sets. Also, the union of these three sets results in the set A union B. We will use this fact to obtain our original relation. It follows that the number of elements of set A union B is equal to the sum of the number of elements of each set taken independently. We will add and subtract n of A intersection B as shown. From the figure, we can observe that the sum of elements in the sets A minus B and A intersection B is equal to the number of elements in set A. Similarly, the sum of elements of the sets B minus A and A intersection B is equal to the number of elements in set B. Therefore, we get the following equation. Hence, the relation is verified. We will now verify this relation. momentarily. Let's denote B union C with the letter D. This can be written as shown. Now, we will replace the letter D with B union C. The third term can be written in the form shown using distributive law. Therefore, we can write the expression as shown. Now, we expand the second term on the right-hand side. The third term can be expanded as shown. Hence, the relation is verified. We will see some practical situations where we can use these relations. In a village, 150 people subscribe to Indian language dailies, 75 to English dailies, and 45 to language as well as English dailies. Find the number of people who subscribe English or language dailies. In the set theory, the word "and" suggests an intersection and the word "or" suggests a union of sets. Let V be the set of people who subscribe to language dailies and E be the set of people who subscribe to English dailies. Let V intersection E be the set of people who subscribe to English and language dailies. We have to find the number of people who subscribe to either English or language dailies. The number of elements in each set is as shown. We will use this relation to find the number of people who subscribe either to English or language dailies. Substituting the values, we get the number of people who subscribe either to English or language dailies as 180. Let's see another problem. On a particular day, 300 students visit cafeteria. 110 students go there for lunch. 225 students have snacks and 50 students have both lunch and snacks. Find out the number of students who had lunch but not snacks, snacks but not lunch, either lunch or snacks. Let U be the universal set of all the students who attended the cafeteria. The number of students in this set is 300. Let A be the set of students who attended the cafeteria for lunch. The number of students of this set is 110. Let B be the set of students who attended the cafeteria for snacks. The number of students of set B is 225. The number of students who had lunch and snacks is given by A intersection B. The number of students who belong to this set is 50. Now, we will find the number of students who had lunch but not snacks. From the Venn diagram, this is given by the set A minus B. The number of elements of this set is given by the number of elements of set A minus the number of elements of set A intersection B. Using the values, we get the number of students who visited the cafeteria only for lunch as 60. Next, we will find the number of students who had snacks but not lunch. This is shown by the shaded region in the Venn diagram. The number of elements of this set is given by the relation shown. Using the values, we find that 175 students had snacks but not lunch in the cafeteria. Now, we will find the number of students who had either lunch or snacks. This is given by set A union B. This is given by the relation shown. Using the values, we get the number of students who had either lunch or snacks as 285.